Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course, Mathematics for Economics Part 1. Now, the module that we have been covering is of integration. So, we have talked about how integration can be interpreted as area under a curve, and we talked about indefinite integrals. We also talked about definite integrals. And right now we are talking about certain exercises where integration and its tools can be used. And here on your screen you can see one particular exercise. So this is an exercise of definite integral. The question is evaluate integration 1 to 2 and the integrand, that is the function we want to integrate, is 3x divided by 10. Now, how to do that? As we have seen earlier, that if there is a constant in the integrand that can be taken out, so here the constant is 3 by 10, we take that out. So, inside you just have x. And integration of x dx, as we know, it's x squared divided by 2, and the limits are 2 and 1. So essentially what we are doing is 3 divided by 10 multiplied by half of 2 square minus 1 square, and that essentially boils down to 9 divided by 20. Okay, this was a simple problem of definite integral. Here is a problem from finance and economics. A theory of investment has used a function capital W defined for all capital T by Wt, that is W capital T is equal to k divided by capital T and integration 0 to capital T e to the power minus alpha t dt. Here capital K is a given constant positive, alpha is also a given constant positive. What we need to do? Evaluate the integral and prove that W capital T takes values in the interval 0 to k and is strictly decreasing. So there are 3 parts of this problem. Now let us try to understand what is this about. So Wt, okay, in some sense it measures the value of investment, and how this investment is measured, it is remember, it's a function of capital T, right? Capital T is the total time over which the investment will, give some return. So that is the total time span. That is the interpretation of capital T. It is so Wt is a function of capital T, but there are some complications here. There is an integral here, definite integral, and you have e to the power minus alpha t, which has to be integrated over the interval 0 to capital T. We shall later on see that this particular thing e to the power minus alpha t, integration of that has an interpretation of present discounted value, but that will come later on. The first thing that we have to do is that we have to evaluate this. W capital T is K divided by capital T, integration of 0 to T e to the power minus alpha small t d small t. Now, this is not very hard to integrate. Basically, you have an exponential function whose power is minus alpha t. Alpha is a constant. So, we know how to do that. It is e to the power minus alpha t divided by the coefficient of small t, and the coefficient of small t here is minus alpha. So, that is coming in the denominator, right? And in this context, capital K and capital T, they are sitting outside because they are not functions of small t. All right, and we have to take the limits value at the limits and minus e to the power minus alpha capital T minus of e to the power minus alpha multiplied by 0, right? And you have to be careful that there is a negative sign here. So, this basically boils down to this: capital K divided by capital T multiplied by alpha multiplied by 1 minus e to the power minus alpha capital T. As you can see, this expression is a function of capital T. That's why you have W as a function of capital T on the left hand side. So, the first part is done. Now, what we need to show is that Wt takes the values in the interval 0 to capital K. Okay. What is the range of capital T? Right? Depending on the range of capital T, W will take different values. Right? Now, we have been given this information that capital T is not negative. It always takes a positive value. So, it basically varies between 0 and plus infinity. So, we can take these two limits and try to see how the value of the function changes. Functions means Wt, how Wt changes as capital T takes these two extreme values. Okay, that's what we have done here. As capital T goes to infinity, that is positive infinity, this is the form of the function. You can straight away see that capital K divided by capital T, this term goes to 0, right? So, the whole expression will go to 0. So, capital Wt goes to 0 as capital T goes to infinity. Now, that is one extreme. What about the other extreme? The other extreme is, suppose capital T approaches 0, the minimum value. We know that capital T is positive, so it can go as close to 0 as possible from the right hand side. Now, so we have to evaluate this. To be more precise, T tends to 0 plus. Now, this we can evaluate by applying the L'Hopital's rule, right? So, we differentiate both the numerator and the denominator in this expression with respect to capital T. And if we do so, basically Wt becomes this expression, which is capital K multiplied by e to the power minus alpha t. Now, we can take the limit, and if we do that as t goes to 0, then this term becomes 1. It goes to 1 because e to the power 0 is 1. So, the value of the function approaches capital K as t goes to 0. And that was our second task, because what was the second task saying? That this function takes value from this range 0 to k. That's what we have shown here. If t goes to 0, the value of the function approaches k, and as t goes to infinity, the value of the function approaches 0. Now, we are also given the information that k is positive, and as we can see that if k is positive, then as t increases, right, it seems that the function is declining, right, in value. It started from k, which is positive, and it goes to 0 as t goes to infinity. Now, we are not sure whether it is a monotonical decreasing function or not. For that, to show that, and that is the third task actually, that it is strictly decreasing, right. So, for that I have to take the derivative of the function, that is derivative of Wt function with respect to capital T. Okay, so that's what we have done here, and we simplify this expression, and it simplifies to this: k multiplied by e to the power minus alpha capital T divided by alpha capital T square, whole thing multiplied by minus of e to the power alpha capital T plus 1 plus alpha t. Now, this expression turns out to be negative. The reason being, e to the power alpha t is always greater than 1 plus alpha t. So, this is true, e to the power alpha t is strictly greater than 1 plus alpha t, which basically means that this expression is negative, right, and that essentially proves that the function, that is Wt, is declining in t, right. So, that was our third task. All right, now we come to some applications of integration. In particular, definite integral. We will be concentrating more on the applications of definite integral. Suppose at time 0, t is equal to 0, extraction from an oil well, right. So, this is a problem of extraction of oil from an oil well. It starts extracting at time 0. The well contains capital K barrels of oil at that point of time, that is at t is equal to 0. The oil well contains capital K barrels of oil. Let us suppose x t, so it is a function of small t, is the amount of oil in barrels that is left in the well at the time small t. So, think about this in terms of a diagram. Here you have t is equal to 0. Now, here how much oil is there? Suppose this is capital K. Now, and take another time, let us suppose generically small t is the time. Now, here what is the amount of oil that is left? Let us denote that by x t. So, this is the value of the oil, or the amount of oil that is left in that oil well, as let us suppose this is denoted by small x t. Small x t is a decreasing function of t, right. How much oil will be left in the oil well, that goes on declining, because extraction is taking place at each point of time. To begin with, when time was 0, the total amount was k. So, I can write k is equal to x 0. Okay. So, you can think of this total amount of oil left in the well to be a declining function of time. what is the extraction per unit of time? So, how much oil is being extracted per unit of time, that can be written as minus of x t plus delta t minus x t divided by delta t. Okay. Why is that? The reason is that how much oil is extracted per unit of time. If I assume this extraction rate of extraction to be positive, then notice x t minus x t plus delta t, right, divided by delta t is always positive, because with time the value of the x t is declining. So, this term will be positive. Okay. So, this is going to be a positive expression, and so the rate of extraction can be given as minus of okay. And now, if x as a function of t is differentiable and as t goes to 0, the above expression approaches to minus of x dot t, because this is nothing but the Newton quotient. Now, let us denote ut as the rate of extraction at point t. Therefore, we can write this as ut is equal to minus of x dot t, where x 0 is equal to k. All right. Note ut is a flow variable, whereas xt is a stock variable, right. Ut is the change in the stock of oil, and that stock of oil is given by xt. Ut is a flow and xt is a stock. All right. The above two relations can be summarized as follows. The xt, or the amount of oil that is left in the well at point t, is equal to capital K minus integration 0 to small t u theta d theta. What is the interpretation of this? The amount of oil left at time small t, that is xt, A is equal to the initial amount, which is capital K, minus the total amount that has been extracted in the period 0 to t. So, that is given by this, the total amount of oil that has been extracted from the well in the period 0 to t. Remember, u theta is the rate of extraction at point theta. So, if I take the integration of 0 to t, that will give me the total amount of extraction from the point 0 to the point small t. So, we can take a very simple example where suppose the rate of extraction is constant, right, and it is given by, let us suppose, u bar. Then we can play around with the above expression, this expression. So, in this case u theta is equal to constant, it is u bar. So, I can replace that in this formula, and if I do so, u bar will it can be taken out, it is a constant. So, if I integrate 1, it becomes only theta, and so this becomes capital K minus u bar small t. So, this is the total amount of oil left in the well after t amount of time, and this is quite intuitive, because at each time, at each point of time, the rate of extraction is u bar. So, after t point of time, the total extraction will be u bar multiplied by small t. Now, one question that can be asked is that at what point of time the oil well becomes empty. Okay. Now, I can solve that by taking x small t equal to 0 and solve for this t, right. We want to find the time in which the stock will deplete to 0, right, and the stock we know is xt. So, that is why we are setting xt is equal to 0, and I use this formula here. So, k minus u bar small t is equal to 0, and that is equivalent to saying that t is equal to k divided by u bar. This expression that we are getting here, it is giving me the time at which the oil well will run dry. Now, this could have been done directly also, because the total stock of oil is k, and per unit of time u bar is being extracted, which is constant. So, the time that will be required to extract all the oil from the oil well will be k divided by u bar. Now, this problem of oil extraction can be extended in a different context. So, suppose capital F as a function of small t is the foreign exchange reserve of a country at time t. So, what is foreign exchange reserve? Every country has a stock, right, a stock of currencies which are issued by other countries, right. So, for example, India will be having a stock of, let us say, US dollars, right. US dollars are the most accepted currency all over the world. So, India, whatever the foreign exchange reserve it has, will be mostly denominated by US dollars, but there could be other currencies also like euro, or other currencies like the Chinese currency or the Japanese currency. So, all those countries' currencies will be held as stock by India, right, and that stock is called the foreign exchange reserve. Likewise, other countries also have their own foreign exchange reserve. Now, this f, which is a function of t, so it basically means that with time the foreign exchange reserve can go on changing. If it is a differentiable function, then the rate of change in the reserve per unit of time is, let us suppose, given by small f t, which is equal to capital F dashed t. Now, if small f t is greater than 0, it means there is a net inflow of foreign exchange in the country at the time t, right. And if f t is less than 0, it means there is net outflow. So, if, for example, if f t is less than 0, that means that foreign exchange reserve, which is capital F t, is depleting, right. On the other hand, if small f t is greater than 0, then the foreign exchange reserve is accumulating in value. Now, notice I said that this example is similar to the oil well example. It is similar, but not exactly the same. In the case of oil well, the extraction goes only in one direction, right. So, as long as the rate of extraction is positive, the stock of oil that is there, which was xt, will always be declining, right. But here capital F t, which is the stock variable here, can increase if small f t is positive. It can also decrease if there is a depletion of the foreign exchange, which occurs if small f t is negative. Now, over the period T1 and T2, the change in the foreign exchange reserve is given by capital F T2 minus capital F T1, and that we have seen is it can be expressed in the form of an integration. It is a definite integral. So, integration of T1 to T2, and the integrand is small f t dt. In this diagram, the change in the foreign exchange reserve is positive between T1 and T2. So, in this diagram, notice what we have done here. Along the horizontal axis, I have time, and along the vertical axis, mind you, I do not have capital FT, I have small ft. And the area under the curve, remember that was the idea. The area under the curve, this curve, that is small ft, if I take two limits here, suppose the limits are T1 and T2, then the area under this curve f small ft will denote how much the foreign exchange reserve is changing over this particular time frame. Now, in this diagram, I have drawn the diagram in such a way that this area, which is above the horizontal axis, I have shaded that, is more than in value than these areas which are below the horizontal axis. Okay. So, the area above the axis, above the t axis, these are the increment in the exchange. That is foreign exchange reserve, and these are what? These are depletion. Now, the picture has been drawn in such a manner that the total amount of increment is more than the total amount of depletion, right. This area, the slanted shades, that region is more than the horizontal shades region. So, that is why I am saying that the foreign exchange reserve change over T1 and T2 is positive. However, if smaller periods like T1 and T dashed are taken, then the change in the reserve is negative. So, that is quite obvious. So, I take the period from T1 to T dashed. So, this small period. Here you can see that there is this area which is below the T axis, and if it is below the T axis, that means small f is negative, right, and therefore, there is depletion in foreign exchange in this particular time frame. Okay, now we come to a third application of this idea of definite integrals. Let capital Fr be the proportion of individuals in a country with income less than or equal to R rupees per year. So, R here is income per year, okay, and capital Fr is the proportion of individuals in a country with income less than or equal to R rupees per year. So, to give you an example, suppose someone says that in India, 60% of India's population have an income which is less than 1 lakh rupees per year. Suppose that is the statement. So, in that case, here Fr will be like 0.6, 60%, and R here is 1 lakh. Okay. Okay. The second point is this: if small n is the total number of individuals, then n multiplied by Fr is the number of people with income no greater than R. Okay, so this is the second statement. Let us try to understand this statement in terms of that example I have just given. I said 60% of India's population have income less than 1 lakh rupees. Now, I did not say how many people in India earn less than 1 lakh rupees. To get that number, how many people earn income less than 1 lakh rupees. Suppose that number I have to find out. Now, how do I find that out? I have to multiply 60% with the total population of India, right? And that is what I have done here. Let us suppose India's population is, let us take arbitrary figure. Let us suppose this is 100 crore people is India's population. So 100 crore multiplied by 60%, that means 60 crore people in India earn income less than 1 lakh rupees. Okay, so by this manner we can actually find out how many people are earning income less than a particular level of income. Thirdly, let us suppose R0 and R1 be the lowest and the highest income levels, right? So we can imagine there is a minimum income level below which people don't earn. So that is R0. And in the other extreme, there could be a maximum or the highest income among all the income levels in a country. And that highest income level, let us denote that by R1. So all the incomes in the country will lie between these two extreme values, R0 and R1. Now, in general, this capital FR is a discontinuous function because rupees are practically discontinuous. However, it approximates a continuous function if there are large number of individuals. Okay, so this is quite practical that R is what? It is income level, and income levels are measured in terms of the currency of the country. In India's case it is Indian rupee. But income levels are not continuous, right? It could be, let us suppose, 1000 rupees or 1001 rupees, 1002 rupees. So there are gaps, right, between 1000 and 1001. So it seems that this FR function is likely to be a discontinuous function, but one can imagine that there are a large number of people, right? In India's case, it is close to 140 crore people. That's a huge number. So one can actually say that this function approximates to a continuous function. Okay, let us assume a particular function which is small fr, okay, which is the derivative of capital FR, and suppose this is valid for all levels of income in this range R0 to R1. Then actually there are standard names for these two functions, small fr and capital FR. They are called income density function, that is small fr, and capital FR is called the associated cumulative distribution function. So one is density, the other is distribution. Okay, now let us pick up two income levels A and B from this range, that is R0 to R1. Then the proportion of individuals in this range will be, this is very easy, it is definite integral A to B FR dr, right? FR is the income density function. So, and this was obtained by differentiating the distribution function. So, if I take the definite integral from A to B of the density function, then I get the proportion of individuals who earn between these two income levels A to B. And how many people are there in that interval? So, like the previous case, I multiply this term with small n. Small n is the total number of people in the country. So, this is the total number of people earning income from A to B. But the next question is, how much income are these people earning, right, who belong to this interval A to B? So, that is an interesting question. What is the total income of these people? Okay, let us assume a function which is MR. MR is the total income of all people earning no more than R, right? R is a particular level of income. So, there will be many people who will be earning less than R, right? I want to measure their total income, that is being denoted by capital MR. Let us now consider a change in the income from R to delta R plus delta R. So, the change in the income is delta R. Now, there are approximately n multiplied by f of R multiplied by delta R people in that interval. Okay. How am I saying that? Fr multiplied by delta R is the proportion of people, approximately this is the proportion of people in that delta R interval, right, and I am multiplying that by n. So, n multiplied by Fr multiplied by delta R is the number of people who belong to that interval. And what is their combined income? So, these number of people are there, but what is their total income? I can multiply that with small r, right, because I am taking the value at r. So, I can multiply that with the level of income, which is r, and that will give me approximately the total income earned by these people in that interval, delta r interval. In other words, I can write this: m of r plus delta r minus m of r. What is the left hand side? It is nothing but the same thing that we are talking about. It is the total income of the people in that interval, delta r interval. It is m of r plus delta r minus m of r, and that is what we have just discussed. It is roughly equal to r multiplied by n multiplied by Fr multiplied by delta r. Now, we can divide both sides by delta r, then the left hand side becomes the Newton quotient. And if I take the Newton quotient and take the delta r approaching 0, then I get m dashed r on the left hand side, right. Okay. So, from here I can get m of r plus delta r minus m of r divided by delta r, and limit delta r going to 0. On the right hand side, it is simply r n and f of r, and this is nothing but m dash of r. So, that is what I have written here. M dash of r is equal to n r multiplied by Fr, or the total income of individuals earning between the limits b and a is this, okay, because this is the derivative, right. Okay. So, remember, if I take the integration, definite integral of the dashed function, that is the differentiated function, which is m dashed r here, then I get the total income of the individuals between that interval. Okay. So, that is what I have done here. I have taken integral of a to b of this function. N will come out because n is a constant, and what is the variable of integration? It is r, because r is changing. Okay. That is, the income level is changing. So, we have found out the total income of individuals earning income between two limits a to b. It is given by n multiplied by integration of a to b r Fr dr. Therefore, the mean income of individuals earning between these two income levels is given by this. So, essentially what I have done is that I have taken this, which is the total income of the individuals earning between a to b, and divided it by the total number of people in that interval, and that number of people, this denominator is a to b Fr dr. that we have just seen before. So, n and n will get cancelled from numerator and denominator, and we are going to get this expression. So, this is the mean income of individuals earning between two limits A to B. An often used income density function is called the Pareto distribution given by FR. So, this is the Pareto. In this case, it is a density function, small fr. It is given by capital B r to the power minus beta. Here beta and B are positive constant. Usually beta has a value between 2.4 and 2.6. So, this is an often applied density function in study of income distribution, the Pareto distribution. Okay, here is a related application of the same idea, demand for a good and income distribution. Suppose the demand for a good in the economy is given by D of P and R. So, demand, that is D, it is a function of P and R. Its P is price and R is income, like before, R is income of the individuals of the economy. So, demand is only dependent on these two variables. The price of the commodity that we are talking about, that price is given by small p, and the income of the individuals. And let us suppose small fr is the income density function. Then it can be shown that the total demand generated by individuals with income between small a and small b is given by G, which is a function of small p, and it is equal to n multiplied by integration of a to b dpr multiplied by fr dr. So, look at the general pattern here, fr is occurring, dr is occurring, but in front there is this the demand function, which is a function of r. You can see the same pattern here also, right. Here we are talking about not demand, but total income of people who are earning between A and B. So, here also you have N FR dr, but here R is occurring just before FR. In this case, it is the demand, because we are not talking about the total income, but we are talking about demand. So, FR is preceded by the demand function, which is D of P and R. Okay, now we come to another, the fourth probably application of integration. The present discounted value of a continuous income stream. Suppose that income is received continuously from T to 0 to T to capital T at the rate of Ft rupees per unit of time at time capital T. So, per unit of time you are getting Ft, right, and the total time in which you are going to receive is from 0 to capital T. The interest is compounded continuously at the rate of R. Let capital Pt be the present discounted value of all payments made over the period 0 to small t. Now, capital Pt is the money one has to deposit at point 0 to match what results from continuously depositing the income stream Ft over the time interval 0 to t, right. This is, we have talked about this, what is the idea of present value. So, here the present value is denoted by capital T. So, it will give me some return over a period of time, and that return must match with the income stream of Ft that I am talking about. Now, the present value of the income received in T to T plus dt. So, I have taken a change of time from T to T plus dt is given by this, right, P of T plus dt minus P of T. This is the change in the present value if I take two different points of time. Okay, that income to be obtained in future, remember this is a present value of some income to be obtained in future. And what is that income that is going to be obtained in future? It is approximately equal to Ft, right? Ft is the stream at point t, and you are changing the time a little bit. So, this amount of income that you are going to earn in future in that dt small period is approximated by Ft multiplied by dt. And the present discounted value of Ft multiplied by dt is what? It is Ft dt multiplied by e to the power minus RT. Thus, P of t plus dt minus P of t divided by dt, I have taken dt to the left hand side, is approximately equal to Ft multiplied by e to the power minus RT. And I can take dt going to 0, and so the left hand side becomes P dash t. P dash t is equal to Ft multiplied by e to the power minus RT. Okay. And so, I can now talk about the total amount of money, the present value of that will be obtained in future. It is given by capital P minus P of 0, and this will be nothing but the the definite integral of this integration of 0 to capital T Ft e to the power minus RT dt. The present discounted value evaluated at t is equal to 0 of a continuous income stream at the rate of Ft per year over the period 0 to t with continuously compounded interest rate R is given by this expression. Okay, so, this is the expression for present discounted value. Remember, we saw something similar in that exercise of investment that we have discussed just now. If the same expression is valued at small t is equal to capital T rather at 0, then we get FDV or the future discounted value. So, here PT is the discounted value when we are standing at point 0 and we are evaluating the future income stream. But suppose that evaluation is done in future at capital T, then what happens? Then it is called the future discounted value. And how it is evaluated? I just have to multiply the PDV by e to the power R multiplied by capital T. Okay. So, in this case FDV is equal to e to the power RT multiplied by the present discounted value, and that simplifies to integration of 0 to capital T Ft e to the power R capital T minus t, because I am taking this inside dt. In a similar manner, the discounted value at any time t is equal to s of a continuous income stream Ft over s to t is given by TV, discounted value. So, here instead of standing either at 0 or at capital T, suppose a person is standing at S, right, and S is between 0 and capital T. Then how does he evaluate the future income stream? So, that is given by this. It is integration of S to capital T, because he is starting from S and the income stream is going to go on till capital T, of Ft e to the power minus R multiplied by T minus S dt. You can verify that here if I change S to be equal to 0, I will get the PDV. Okay, here is an example. Find the PDV and FDV of a constant income stream of 1000 rupees per year over the next 10 years with interest at 10% per annum compounded continuously. So, PDV, I just directly apply the formula integration of 0 to 10, right, 10 years are there, multiplied by the stream of income. In this case it is constant. So, Ft is just 1000, e to the power minus RT, R, that is rate of interest, is 10%. So, it is minus of 0.1. multiplied by T dt. And so the things are now falling into places. So I just have to integrate and take the definite integral. It comes out to be roughly 6,300 rupees. This is the PDV. For FDV, it is just converting the PDV into FDV. I have to multiply that with e to the power r multiplied by capital T. So e to the power r is 0.1, capital T is 10. So 0.1 multiplied by 10 is 1. So E multiplied by PTV, and E is roughly, that is how much is it, 2.72, and that boils down to 17,136. So you can see that there is a huge change in the value depending on whether we are talking about PDV or FDV. Okay, let us do this one and then we shall call it a day. Find the present discounted value of a constant income stream of A rupees per year over the next capital T years. Assuming an interest rate of R annually, compounded continuously, what is the limit of the PDV as T goes to infinity? So there are two parts of this. First, we have to find the PDV. Let us do that. It is simple. I just have to plug in these information into the formula. Here Ft is equal to small a, r to the power minus Rt, and the time span is 0 to capital T. Now this obviously is I have to evaluate that, but notice that this is a function of capital T. So I can write this as Pt, denoting the present discounted value, which is a function of capital T. And I do this integration, and I find this Pt to be of this form: a divided by r multiplied by 1 minus e to the power minus r capital T. Now the second part was this, that as t goes to infinity, then what is the limit of this PDV? Well, I have to take the limit of Pt as t capital T goes to infinity. So this is what we are getting into, and so this will become just 0, because e to the power minus of Rt, t goes to infinity, it will become 0. So this becomes a divided by r. This expression is same as the PDV of an infinite future income stream of small a rupees per year, discounted at r rate of interest per year, but not continuously. So this we have talked about before when we were talking about geometric series, right? There I did not talk about continuous discounting, right? So there was discounting, but the discounting was discrete. So there also I got the same expression, a divided by r is the present value. So here also we are seeing the same thing. The exact example that I gave was that of a bond which pays a return in perpetuity. There the value of the bond or the price of the bond was given by a divided by r. Okay. I think I'll stop here, and I think there will be just one more lecture that will be required to finish this topic of integration. So I'll do it in the next lecture. Thank you for joining us. Thank you.